Let's talk some Ready, Set, Go here. Lesson 5 of Unit 2. So we're simplifying roots. There are a few examples here at the top. And so what we're trying to do is we're trying to find the perfect squares inside of the numbers and bring them out for the square roots. So the perfect squares would be 1, 4, 9, 16, 25, 36, 49, 64, etc. It goes on forever. Those are 1 times 1, 2 times 2, 3 times 3, etc. So for 40, number 1, square root of 40, thinking 4 times 10. So the square root of 4 times the square root of 10. And that would be 2 square root 10. For number 2, 50, thinking 25 times 2. Square root of 25 times the square root of 2. So the square root of 25 is 5, and the square root of 2 has to just stay there. Now when you get to number 3, there is a little index there. The index is 3. Now what that means is that we're taking out groups of 3, or you could call them perfect cubes. So one strategy you might use for this is break a number down to its to its prime numbers. So 16 is 2 times 2 times 2 times 2, all prime numbers. Well, 3 of those 2's get to come out when they're under the root and the cube root. That means groups of 3 get to come out as 1, 2. It takes 3 2's under that root. So it would be a single 2 and then the cube root of 2. That 2 that's out here, that's this 2 right here. See, it can't get out because there's only one group of it. It has to go out in groups of 3. So you'll notice that the evens are all square roots, 4, 6, and 8. And then the harder roots are the odd ones, 5, 7, and 9. So let's do one more odd, one more even. Let's do number 4. So 72, if I can't figure out what the number is, what I can do is I can break it down with this factor tree. I know that's 8 times 9, and 9 is 3 times 3, and 8 is 4 times 2, and 4 is 2 times 2. So as prime factors, it would be 2, 2, 2, 3, 3. Now, if I'm under the root, the square root, groups of 2 get to come out. So 2 2's come out as 1, 2, 2 3's come out as 1, 3, and then there's a 2 inside that's like an orphan. It's stuck inside. So square root of 2, and then I go ahead and multiply the 2 and the 3 together. So it's 6 root 2. Now 81 to the 4th root, 81 is 3 times 3 times 3 times 3. So it has exactly the correct number of 3's to come out. And it comes out as a single 3. That's right, it takes 4 3's under a 4th root to come out as 1 3. Well, let's look at the next section real quick here. This table is a lot like the one we did in class the day before on the Launch, Explore, Discuss, except now we're cubing the numbers. So 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. And on the other side of that, you're going to have the fractions of those. So this would be 1/3, 1/9, 1/27, and just like we did a second ago, 1/81st. Okay, finish and explain the meaning of 3 to the negative 2. Well, one explanation is if we go to the right, we're multiplying. If we go to the left, we're dividing. So 3 to the negative 2 means to take that initial value of 1 and do 1 divided by 3 divided by 3. Now, I know you've never seen something like that before, but you could do this on a calculator, right? You could go 1 divided by 3 divided by 3. It just means repeat the division by 3. Or in a more friendly way to write it would be 1/3 times 1/3. And so there's where we're getting 1/9 from. So that's kind of weird. This actually right here means 1/9. And so does this one, and so does this one. 11. Two expressions with exponents are a perfect match, except one has a negative exponent and the other has a positive exponent, like 5 to the third and 5 to the negative 3. How does the exponent change the meaning of the expression? Well, it changes it from repeated multiplying to repeated dividing. Or dividing. Yeah, I should have said multiplying, but dividing. For problems 12 and 13, use the graph. This is the graph we looked at in the Launch, Explore, Discuss. How does the graph show the relationship? Another word for relationship might be connection between 2 to the third and 1/2 to the negative 3. The connection is they both give you the same number. They're both y values of 8. What is true about the input values for each equation that produce the same value? They're opposites. Simply, they are opposites. Opposites. You know, I just noticed something here that may be a little bit confusing. It said 2 to the 3 and 1/2 to the negative 3. So 2 to the 3 means to go right 3. And so this is why I went, here's right 3, and I went up to here in my thinking. And the other graph, the one that's coming down or decreasing, it's at negative 3. And I went up here to get that point. Okay, so rewriting, we'll just do the first one here. This would just be 3 to the positive 8. Oh, with, sorry, that's wrong. 1 over 3 to the positive 8 has to go to the other side of the fraction if it goes from a negative to a positive. One more. 15. If you have it in parentheses, just flip the entire fraction upside down, and now you can write it as a positive. If you're thinking, what happened to this 1? Well, it's still there. I just don't usually write it. It's 7/4 over 1. And finally, number 18 in the go, find the indicated value for the problems. F of negative 3 means to put negative 3 wherever you found an x. So negative 6 minus 7, the value is negative 13. Find, part B, find x if f of x equals 21. So that means that this expression, 2x minus 7, equals 21. It's actually an equation to solve. So if we add 7 to both sides, we'll get 2x is 28. And divide by 2, we got 14. And then finally, can you put in fractions? Sure you can. F of a half is 2 times a half minus 7. That's 1 minus 7, or negative 6. Well, I hope that helps. We'll see you next time.